jump through the SOP. So first of all, pre-flight check. A lot of this is fairly straightforward kind of stuff. The first place where you can actually see something is in the Avantage software, which looks like this little Illuminati symbol. So it's right down here. I'm going to bring this guy up, and what you'll see are a couple of different kinds of regions, or a couple of different kinds of features. But in particular, what I'm asking you to do is to go to the sample tab and then the vacuum details tab so that we can confirm the health of the vacuum state. So sample tab is this little guy, and then vacuum details guys is there. So let me show you that in Avantage. So here we're going to go to sample tab, vacuum details tab. Once I click on that, it actually pops up on the other monitor, so we drag it over, and now you can see where we are. What I specifically asked for in the SOP was, I want to see in chamber less than 1E-8 and load lock less than 1E-6, both of which are satisfied. I also want to confirm that all sources are off, and you can see that those all have a black little spot, down here. So there's no sources turned on. The nature of this instrument is that you often configure it for a long experiment, something that might take several hours. You hit the go button and go get a coffee or do something else. And so you want to make sure that you always have a gun turn off or a gun shutdown operation at the end of every recipe, so that you don't needlessly waste time or lifetime on any of our sources. So basically, I'm asking you to confirm all the sources are off and that the vacuum state is healthy. And then if your samples are known to outgas, you might need to outgas them in our little vacuum oven that we have here in the lab space. Otherwise, you need to leave sufficient time for it to sit in the park position of the load lock and outgas there before you transfer into the main chamber. So now I'm moving on to slide number 14 on the SOP, which is mount sample. It needs to be configured for the relative height range of your specimens. We left it at the 0 to 5 millimeter thickness because you guys are typically doing thin film stuff. You're going to attach that to a top plate using these clips. There's different top plates for different sample sizes. And then one important thing to keep in mind is that please don't put anything that's going to create an additional vacuum or outgassing load in the chamber by utilizing adhesive or any kind of tape on the top plate. If you really need to move your material into the system on some sort of an adhesive backing, then I would ask you to put that on a glass slide and then affix the glass slide to the top plate. So I just don't want any sticky residue on these things that will compromise the vacuum. Additionally, the samples and clips cannot extend past the end of the top plate, and all your samples should be approximately the same height to avoid source shadowing. We shouldn't have an issue there because we only loaded one sample. All right, moving on to slide number 15 in the SOP. We go to load the samples. We have to basically get them into this depth gauge and swing the arm across. As long as it clears, you're good to go. This is very similar to loading samples into the SEM, making sure that you have clearance before you try to transfer through any load lock or other gate valves. Once we're done with that, check process, we vent the load lock and open the door. We then place the little sample holder in here, and the two positions on the bottom side are keyed. They can only fit one way into here, so please make sure you get that right. And then you would basically pump down your load lock, so close the door, and send the sample to what they call the parking position, or the park position. This is where it may take up to 45 minutes of time in order for your sample to sufficiently outgas. What I'm asking you to achieve is 9E-7 millibar in the load lock chamber before you move it to the analysis chamber. All right, so that was all done Thursday, pumped down overnight. We had another group session this morning where we moved it into the sample, moved the sample into the analysis position. So we basically went to this screen in here, and we're able to click on this icon to move it into the analysis chamber. And now we're basically at a spot where we can pause and start playing around and look at the navigation view for the system. So before we go any further, does anybody have any questions about how you're going to check the tool when you first show up, how you're going to mount your samples, or how you're going to load your samples into the load lock? Any questions there? All good? All right, so let's move on. So now we're under navigation, and we're going to get there by going to the main command toolbar, which is always on the left-hand side over here. And we're going to use our optical view and one of several tools to identify the best place to measure on our specimens. We're going to go through each of those. I'm going to move this guy out of the way. I'm going to go back into our optical field of view by clicking on this one. And what you can see is that right now, we've defined from a different experiment a series of different positions on which we made some measurements. And then, Nishal, here's your sample hanging out right over here. I don't really know what this is in this spot right here. It almost looks like there's an interface that has formed between the two different portions of where we clamp this specimen. Is this contrast something that you're used to seeing on your specimens?
No.
Okay, well, that's very interesting. So we'll have to go see what that all means. All right, so if we want to basically start navigating around our specimen, there are 3 different spaces in here that you need to pay attention to. The first is this picture, which was taken when we loaded the sample into the load lock. This is called the platter view, and it is intelligent in that I can click on any arbitrary position, or rather double click on any position within this field of view, and it will drive the stage to that point. Right now, the stage position is indicated by a little red cross, which is hidden behind this data point. What I'm going to do right now is I'm going to move over here to this position, double click, and what you can see is that the stage is now moving. You see the little red cross updating its position? And if I turn my lamp on here, I should be able to see that I'm sort of moving across some stuff on the stage. So I'm translating over. Right now, I should see this big giant plus sign cut out, come into my field of view. And then there's the F. Everybody see that right there? All right, so this is one type of illumination. This guy is what you would call your coaxial light. So it basically comes straight down through the same path as your camera feed. And so on specimens like this that don't have a whole lot of asperities or roughness sticking off the surface, you don't get a whole lot of contrast here. So one other option you have is to not illuminate the sample in a coaxial fashion, that is along the same axis as your optical capture, but rather illuminate from the side. And now, as you can see, there's my little slider right here, I get much better contrast for sort of depressions or particles or things sticking off the surface. So this guy is your platter view. This is your optical view. And the 2 sources of illumination inside the chamber are coaxial light and side light, with slider bars to adjust the illumination as you see fit. This little guy right here only turns the bench lights on just above the load lock port. So it's just for making sure you have enough light whenever you're loading something into the load lock. I'm going to turn this guy off. Okay, so as you've gotten to this point, you can sort of see what samples you have loaded into the chamber. And then essentially what we need to do now is get to the point where we can focus on our specimen. So we have several different fields of view that we can use. We're operating these tools to get our sample into focus. So that's sort of the next spot. So you have the option of using these plus and minus Z and plus and minus magnification to change your live view area and get to where you think you're at the best focus. There is an additional camera, a side mount camera, that you can utilize at a different angle, and this is the little button that you use to toggle between those 2. Let's play around with that. This guy is my current optical field of view. I've already set my illumination, so I'm now going to use my plus and minus Z buttons to focus in on the sample surface. And you can just basically cross back and forth between whatever you think sample focus happens to be. You can change your magnification if that helps. And then additionally, if I just jump right over here, notice I can also click in my optical field of view, and it'll just toggle to those spots. Turn down my illumination just a little bit right here. And I can also switch to the side view camera. It looks something like this. Now this isn't so great of an image right here, but remember this is a little bit more zoomed in. And so I can basically adjust this guy with a couple of different tricks up my sleeve to try and get to what I think is a close approximation of optical focus. Now you don't have to worry about this too much because the tool is going to do an auto height range finding whenever it goes to each individual point. So if we wanted to go in and just sort of get close, that helps it find focus whenever it starts actually interrogating the specimen. All right, so let's move over to the actual sample. Again, I can double click in the field, or I can use these little buttons to drive myself to various spots. And now, as you can see, I'm sort of right on the edge of this top portion of the specimen right here. So I'm going to want to refocus on whatever I think the edge of that coupon happens to be. So that's right here. I'm going to go and drive up. I know the focal point has to be somewhere up here. Now we have what looks like a little bit of an edge, kind of a feature right here. We'll try adjusting our lighting. And that looks like some grain structure that I see on there. Is that what you're used to seeing on these samples, Nishal?
Yep.
Good. So this would be sort of a corner of your sample. Again, I can drive over here by clicking on the platter view, and we can just see if there's an obvious change in the contrast as we get over here to this. So it looks like a delaminated side. So that was the interface. There's the metal clip. Yeah, I'm not sure exactly what's going on right there. Down here, there's another interface right about there, where something has happened between these two positions. Didn't help much. Yeah, again, there's some kind of an interface right here. I don't really know what's causing that. But we probably want to go ahead and measure somewhere out here in the meat of your specimen. If I go back to this far edge, we know that we saw something that was indicative of some kind of a pattern. I think this is the underlying portion of the stage, the top plate you're seeing just through your film, because it's on a transparent substrate. So based on the contrast that you see here optically, this might be one thing that you can use to identify both focus and region of interest. One other thing that you can do is to try to map out where the elements of interest exist and not rely solely on optical contrast. So that's the last thing I'm going to show you here. If I reference this part, again, we're just trying to get it into some sort of a focal point, but you can also utilize elemental mapping to figure out where the elements of interest happen to be on your specimen, or if there's some sort of a weird inhomogeneity that you weren't aware of. So we're going to go through this little snap map process, and that's on page 18 of the SOP snippet that I sent you. So if I go into this spot right over here somewhere, and I just try to go through what I think is appropriate focusing, I just want to get fairly close, and then what I'm planning on doing is executing a snap map solely for the purposes of trying to navigate and sort of determine contrast in a region of interest for my sample. So when I go to utilize snap map, the first thing I need to do is go and configure the snap map before I run it. So I'm going to come up here and click on the snap map settings. That's going to ask me several different kinds of questions, and I'm going to pull this the same thing back up here. So what it's asking me for essentially are things like center energy, which I typically select by choosing an element. So Nishal, if you had to pick an element of interest here, something that would be conclusive evidence that you were staring at the right place on your specimen, what element would you choose? Lead?
Lead, iodine.
So you want to, well, you can only pick one for a snap map. So you want to pick lead, or you want to pick iodine?
Let's pick lead.
Okay, so lead. Now if I click on lead, it will automatically dictate the center energy. I need to give it an image resolution, which is a pixel count. You can see an example of a snap map up here. This one was taken with a 50 by 50 pixel array. So there's 50 pixels this way, 50 pixels that way. What this is going to do is essentially take a series of really, really rapid scans with a very short dwell time and reassemble them into this map. Each pixel shows essentially a relative scale of intensity for this center energy only. So I'm only looking at this specific center energy at this point. The only other thing I need to dictate essentially is the size of the map in square millimeters. Or sorry, it'd be the length of a side that's going to be a square in millimeters. Here's your scale bar to indicate the size of the spot in microns. So if I execute a snap map, it will conduct this scan in an area centered on this spot with this dimension as one side. So if, for instance, I want to interrogate something like a 0.5 millimeter by 0.5 millimeter, that would be a box with this length on the side, so right about there. Okay, I could also make it slightly larger, but for the purposes of this, let's just go through it and see if there's any differences. So if I click on OK, my snap map is now configured, and I can run the snap map centered on this crosshair position. Everybody ready? So we're going to run the snap map. It's going to check the X-ray source, and you can see over here this little blue flashing. It's bringing the X-ray source online. It may take 5 to 10 seconds for it to do so, and you'll notice that the pulsing starts getting faster, faster, faster. Eventually it will turn green, and then we'll see the stage start rastering across its 0.5 millimeter by 0.5 millimeter square. So again, this snap map function, at least for the purposes of navigation, is solely for you to help identify regions of interest based on elements present rather than optical contrast. So there it goes. It's just basically connecting those snap maps, and it's kind of driving through and updating the snap map up here in real time. So if there was a question as to, well, where is the stuff on my sample, this is a way to determine that with essentially utilizing photoelectron counts. It doesn't look like we have a lot of inhomogeneity here, so would it be correct, Nishal and or Craig, to assume that this sample should be homogeneous and I can basically shoot anywhere I like?
Yes.
Okay, fair enough. So we don't see a whole lot of contrast here. Just so you have a, an example of the kind of contrast you might see, let's run it over here and do the same thing. So we'll run one more snap map over here. So you see the difference, right? Clearly there's where I have lead and a spot where I have no lead, right? And it's a pretty obvious line. So snap maps are also useful for sort of spatially resolving the position of certain elements, or rather the photoelectron response from certain elements within your specimen. And of course, you can make this have better and better spatial resolution by limiting the spot size of your X-ray source. But does that clearly enough convey the what the snap map is for?
Yes.
Okay, so we'll go ahead and you'll let this finish. If you did need to stop the snap map, you can do that here. And essentially, it seems like we can drive to any arbitrary spot over here and just pick a place for analysis. Great. So we've kind of figured out a region of interest for our specimen. And so, with or without snap map, you can use optical contrast. You can use one or more camera feeds. Either way, you've figured out where you want to do your analysis. You've figured out a region of interest, and you've got it in your field of view. If you wanted to, for some reason, capture this image or capture this snap map or even this platter view, you can always right-click on any of these guys. You can right-click on this guy and save the image. If you save it as a PNG or just a JPEG or something, you'll just get this image. If you save it as a .dgd extension, which is what this Avantage software is able to understand, then it will preserve the scale bar, and so you can keep that in your reports if you think that's necessary. All right, so we've utilized whatever tricks we need to figure out a region of interest, and now the point is to get to a definition of some kind of an experimental workflow. So within the SOP, referencing now page 19 or slide 19. Which is effectively page 7 in this SOP, we're going to now go in and start configuring the experiment. And the thing that you want to remember is that the experiment is going to be laid out like a tree, so something with a defined hierarchy, and there's a specific methodology by which you sort of build the experiment, and it's based on the levels of the hierarchy. So you always want to make sure you're adding things in the following order. You want to put a source first, then points, and then skeins. So let's take a look at what that means. So again, if you can follow along on this slide, I'm going to move it out of the way. The general idea now is that I'm going to go to the experiment tab, which I can get to here. I can also get to it there, right? And this was a previous experiment that somebody else was running. They've already concluded it, so I'm going to do File, New Experiment, Brand New. So the first thing I need to do in my experiment is go in here and figure out where I'm going to save this thing. I do not, in fact, want to save it under the roads group. I'm going to go all the way down here to the D drive, shared data, and there is Zakharov group right there. Boom. Okay, I can make a sub-project folder underneath it if I so choose. It's going to make that for me, and then I can do a project description. This is, test run, whatever you want to call it. You can also come in here and change the name so it's not something stupid and arbitrary like experiment. So, for instance, you might put in 2007 17. And this is, MAPI test run, whatever you want to call it. Down here, you can put your sample name, Z123, whatever it happens to be. You can annotate this as you see fit. And essentially, you're defining the, where all the stuff is going to save. What we're ultimately going to end up with here is an experiment that you guys can utilize over and over again. The only thing you'll need to update are the actual positions you want to scan. So we've added the experiment, and we've basically saved a save location where it's going to dump all our data. Now what we need to do is go in and add a source. So again, on that page 7, slide 19, you can see that we're going to click the source insert icon. And over here in my experiment viewer, you can see that the source insert icon is this one. All the other ones, note, are grayed out. So I cannot insert any points, nor can I insert Spectra, because I haven't yet defined a source. So the first source that we're clearly going to want to use is an X-ray gun. Boom. Now I've got my X-ray gun inserted here. And when I click on this particular item within the experiment tree, notice that the field of view down here changes. So when I go into my X-ray source, there are 2 key things that you need to configure. The first is, what spot size do you want to use for the X-ray source? And do you want the plug gun to remain on for charge neutralization? So regarding the first, you can modify the spot size in 5 micron increments, all the way from 10 micron diameter to 400 micron diameter for the X-ray spot. Obviously, the larger the X-ray spot, the less spatial resolution you get, but more counts. So, and also to some degree, you'll lose the tightness of your resolution, though that's a little bit more related to pass energy. So, if we want to stick with a 150 micron spot size, that's fine. If you want to go with the full size, you could change that here. Something like 400, and then just simply hit apply. So now that I've configured my source, I can go in and now start putting in actual regions of interest to measure. So when I've clicked on the actual source, or it's highlighted, now you notice that I can insert either a point, a line, or a map, or an area. So let's just go with a point. It's going to be a single data point, boom. And it will center it on the crosshairs wherever I'm sitting right now, with its associated X, Y, Z, and azimuthal positions stored under the position tab for this new point object. Okay? Now, this is not particularly descriptive. So again, same thing, you can come in here to general and put top right corner of mapping slide. Right, or whatever else you want to call it. So you can update these things, and again, the point or where it's going to actually take the data is centered on this little green crosshair, which is also now updated within the platter view, such that if I end up moving off of this point for some reason, I can always move back to it and center back on my field of view. This ellipse is intended to show you basically the footprint of the X-ray beam. So if I go back in here and change this to something like a 100 micron spot size, now you can see that the footprint of the X-ray beam is much, much smaller. Okay. Okay, so we have configured the experiment. We've put a source in place. We have defined our first data point. And now what we want to do is go through and define scans. So again, it's always source, point, scan. So you define them in that order. So now that I'm on this point, I can say what kind of spectra I want to collect. So in the SOP, we've basically gotten to the point where we've inserted this X-ray source. You can also do an etching or a depth profile here, so we'll revisit that in just a minute. This is how you basically go in and add points, so slide 21. So now that I'm selected on this, this point source, notice that my scan icon is now no longer grayed out, or spectrum icon. I can click on spectrum, And the one I would suggest you use in the, until you're completely comfortable with the machine is the multi-spectrum option. When you click on multi-spectrum, it's going to pop up with a similar little dialog box like we saw before with the snap map and say, hey, human, what are you trying to look at here? And what we want to tell it is, okay, system, I'm interested in something that has these following, possible elements in it. And so I'm just guessing here, but I would imagine on this particular sample, you're probably keenly interested in a position or response from lead, from iodine, and then likely a series of other different kinds of contaminants, something like carbon, oxygen, possibly nitrogen, chlorine, maybe something else that you guys have built in there. I don't know what halogens you're playing with here, but we need to select every element of interest before we move further. So other than carbon, nitrogen, oxygen, lead, and iodine, is there anything else that we should be searching for as far as the composition of your specimen?
Can we select hydrogen?
Hydrogen?
Yeah.
What transition would we be looking for hydrogen?
Because it has CH3, NH3, it has carbon, hydrogen.
No, I understand that, but think about what you're trying to look for there, right? What is the transition energy for a hydrogen electron, right? So are we really sensitive to that or not?
Probably not.
We'll see what it tells us, right? So that's more of a theory about XPS kind of a question. Are you familiar with XPS, Nishal?
Not really.
Okay. So one other thing I just want to point out very briefly then, just to make sure that's clear. I think I might have accidentally closed it. Yeah, here it is. So this thing is a really nice place to start. Just remember the URL, xpssimplified.com. This is actually Thermo's website, and you can come in here and click on all kinds of stuff within a periodic table view, or even just go back and look at, what in the heck is XPS? But these different things will sort of give you a knowledge-based kind of overview of what's known about the different spectra for instance, chrome or lead or iodine or whatever element you're looking for. That way you understand where should I be expecting these kinds of binding energies, which portions of the spectrum. When it comes down to it, you really don't need to know all that stuff because this is referencing the exact same database. So if I want to add different kinds of spectrum in, there's a couple of different things you want to kind of keep in mind, and most experiments are run this way. You're typically going to have a survey spectrum that has a full-on range to measure basically an overview of all of these peaks all at once. To do that, you can insert a survey spectrum by clicking on this box. So it will then take, it'll then sort of look at all the elements of interest right here and pick the highest and lowest binding energy values and make sure that your scan covers all of this region of interest. Okay.
But also be nice to check for tin and lead because that's in the substrate.
Tin and lead, very good.
Yeah. Or sorry, I mean, was it indium and tin? Indium and tin. Yeah, indium and tin. Yeah, that's right.
Well, if you're interested in the valence band edge for this particular specimen, you can also insert this. That's typically a scan right around 0 to 50 EV. It's also a much longer scan because it's one of the weaker signals you'll try to detect in one of these systems. So we can go ahead and insert this guy just for fun, and we can disable it if we don't want to use it. You can do an energy offset if you really want to. I would argue against doing that unless you have some compelling reason to do so. And then finally, you have to define what kind of spectrum type are you really trying to do here. Now, I'm more interested in the sort of a high resolution kind of a scan, and that's this default guy right here. A snapshot typically has a very, very short duration. It's meant for doing things repeatedly very, very quickly, like doing a line scan or doing an area map or doing a depth profile. So just quick shot, quick shot, quick shot. You're not going to be doing a lot of modeling on these kinds of snapshot spectra because it's just kind of choppy. There's not a great signal to noise ratio there. It's really meant for something that's fast. And a snap map will basically do the same kind of thing right here, except it'll capture that as your data. You typically want to do snap maps inside the decision or the experiment tree whenever you're dedicatedly trying to identify the spatial location of certain elements in your specimen. So that's what that's for. So we're going to leave this as scanned. We're going to tell it to put in a survey spectrum and put in a valence spectrum for us. These are my elements of interest. Thank you very much. And we hit OK. And now you can see it's just going to look at all the elements we had selected and just populate them over here. So let's step through each of these individual pieces and make sure we know what we're telling it to do. So the first one is the XPS survey Spectra, which I've highlighted here now. So down here, again, this little window is going to change depending on what you clicked on. The first thing you see is that it's using binding energy as its sort of scale. It's going to start here and end here. If you don't like thinking about it that way, you can click on either of these buttons, doesn't matter, and it'll give you a center and a width, which is another way to sort of look at it. So as you can see, this thing has a gigantic overall width, and at 1 EV per step size, it's going to have to go through 1361 overall channels to capture this survey spectrum. It will do so with a pass energy of 150 EV. It's going to scan through this entire energy range twice, and it will stay for 10 milliseconds to collect signal at every single one of these individual steps. Not sure if I went through that too fast. Does anybody have any clarification questions on what you're telling the scan to do in this screen? And just to be clear, it knew to set up this overall range based on the elements of interest here. Okay? I'm going to grab the valence band scan. So I just highlighted it here. I can click and drag. It just bothers me. I like having it down here at the bottom. So I'm going to move this thing up to here. Thank you very much. And so now let's move on from looking at the survey spectra to each of the individual spectra. Notice the gigantic pass energy here. This is essentially inversely proportional to resolution. So your survey scan is not where you go to fit data or try to get full width half max or refine position. This pass energy is not going to give you enough fidelity to do something like that. The individual scans that you then go back and do after you've done the survey scan are where you're going to get your high resolution data. So this one, for instance, the lead 4F transition has a pass energy of 50 EV. It's going to scan it 10 times instead of 2, and it's going to dwell for 50 milliseconds as opposed to 10 milliseconds. Okay? It also has a substantially lower energy step size. Now, I would argue that this is actually probably even a little bit too large. So I would change this to maybe something like 20 EV, unless there was a compelling reason for me to be worried about not capturing all the lead 4F activity in this overall range, which is this width. Okay? If you wanted to look up any information about lead before you started this experiment, you can go to your XPS knowledge view screen right here. You can go to your periodic table and say, hey, tell me what you know about lead. And so you can see here that lead metal is centered at about 137, and depending upon what you stick on the lead, right, it can shift it what looks like about 3 EV in either direction. So a pass energy of 20 EV for this lead 4F transition is probably more than enough to catch, some of this other stuff, unless you're worried about these other weird loss features. So again, I can just kind of look and say, well, I'm going to center this scan somewhere around 143, so right about there where I expect this 4F 5.5 transition, and then I'm going to go 20 EV for the overall width. So I'll go 10 in this direction and 10 in this direction. If you think that's enough to catch everything you're sort of interested in, like you're worried about this tail, you might want to increase this to 25. If you do that, remember that you're giving up some resolution. All right, so other than changing the pass energy here because I'm being persnickety, we don't necessarily have to change anything else about this, unless you just don't like how the data looks. It's also incredibly important to remember that if you are going to analyze and compare spectra together, they must be collected all with the same pass energy, or you don't have the same overall resolution to the scan. So same energy step size, same pass energy. So if I'm going to make this modification here, I really need to make it at every single one of these subsequent guys here. So let's step through that now and make sure that we can do that. So there's the lead 4F. Now I'm going to click on carbon 1S. You should probably have this in every single scan you ever do. I'm going to change this to 20. And again, if I didn't know where carbon 1S was, I can come back here to my knowledge view, click on this guy and go, hey, thing, tell me what you know about carbon. And there we are, right? Centered around 284 or so. And then I should be able to see everything that I need to see about carbon-carbon, carbon-oxygen-carbon, or carbon-oxygen double bond oxygen within that overall 20 eV range, or the 20 eV pass energy. Okay, moving on to nitrogen, same thing. Okay, here, indium. And if you guys have any specific knowledge, or if in the standard data that I sent, there is a different scan condition that you prefer to stick with, please let me know. But ultimately, what your group is going to want to do is generate this kind of experimental sort of setup or outline or workflow, and just use that same data collection methodology each individual time. The only thing you'll have to come in and do is update your actual position for a new region of interest on your specimen. Or for that matter, you could copy all of this and make an exact copy of a new data point for a different position in your specimen. Maybe you want to do center and edge. I don't know, right? Because these are spin cast films. There could always be some difference. All right, so we got all the way down here to oxygen. That one's done. This one's done. And then finally, we're at the valence band edge. Note that when I go from a standard elemental transition scan to the valence scan, the dwell time stays at 50 milliseconds, but the number of scans goes up to 20. Everything else was just a scan of 10. Valence electrons are going to be some of the least populous species you generate, and for that reason, you want to make sure that you leave a sufficient number of scans to freeze out any noise. Let's go ahead and do 0.1 to keep the energy resolution the same. And I would say for this guy, you could leave the pass energy at 50 EV. That basically means that it's going to go from -5 to about 40 EV to try to catch those valence electrons. You'll kind of see what those look like. It's sort of a little tail right close to zero EV. All right. So from this stage, we've started an experiment. We've configured a source. We've configured a point. And we've configured the scans that are associated with that point. Anybody have any questions about this kind of hierarchy? So notice that experiment has multiple sources. Sources can have multiple points. Points can have multiple scans. But they all have to be nested in this hierarchy.
Yeah. Let's see, what other sources are there? Are there other sources built in?
Excellent question. So let's go back to our experiment and see if we can insert a different source. The other kinds of sources you would insert here would be a UV source. This is going to use helium to generate UV electrons, and this is going to be for doing UPS analysis. We also have ISS, which is an ion ionization source. So it stands for ion scattering spectroscopy. In this case, what you're doing is ionizing a helium atom and directing that towards the surface. And what you end up doing is biasing your hemispherical analyzer not to select for the energy of a negatively charged species like a photoelectron, but rather to select for the energy selecting for energy of these effectively alpha particles or helium atoms that you've ionized and bounced off the surface of your specimen. So this, Nishal, is a much easier way to try to account for the presence of lighter elements. And what I would urge you guys to do, because I haven't actually had formal training on this one with the applications guy, is go take a look at that XPS simplified webpage. And if you go underneath here, you should be able to find something about ion scattering spectroscopy. Yeah, they're pretty proud of their stuff. I'm sure it's in here somewhere. Okay, last one, Craig, to finish out the answering of your question. So in addition to the X-ray source, the UPS source, and the ISS source, you would also have the option of using an argon gun. That's not used to actually collect data, but rather to condition your specimen. When you insert a profile, this little guy right here, that allows you to either just use the ion beam to etch the surface of your specimen to, say, clean off adventitious carbon, just to get it ready for your standard analysis, or you can do a full-on depth profile where you give it a set of conditions for how long do I etch, with what energy and current condition, and how many times do I repeat this individual step, if you will, whilst inserting a scan in between every single one of these etch runs. So in that sense, you can use argon to mill away a fraction of a nanometer of your specimen and then recapture the data after every successive etch operation to put together, essentially a chemical or a valence state map as you move through the depth of the specimen. And that depth profiling can be done with either monatomic argon, which is best for moving inorganic species out of the way. We also additionally have the option of using a cluster source, which is supposed to be better for milling through things like polymers or organic compounds. All right, did that answer your question sufficiently?
Yep. Also, one other thing I was curious about, why did the pass energy have to be the same for all the atoms again?
In general, you want the pass energy to be the same so that all of your scans have essentially the same resolution of, when you're comparing a point-to-point values. So if your pass energy is radically different on the different spectra, then when you start trying to compare spectra to each other, you may have difficulty with the number of data points in a given curve.
But see, the resolution, that's just decided by the step, right? The 0.1 electron volt step.
Yes. Well, let's go back and see if I can make sure I'm clear. So, for instance, if I give it a center energy and a width, right? If I change this pass energy to 25, that's going to. Why didn't it update this one? Interesting. Let me see if I can find in the specific portion of the manual where they talked about this process. All right, so snapshot spectra have 150 EV. So that defines the spectrum width. So for snapshot spectra and or snap map spectra, changing the pass energy also changes the width. So I think I may have been mistaken. That is not the case with scan spectra. So,
okay.
So it's my mistake. Only the snapshot spectra have the pass energy tied to the width. So they're just linked. In the standard spectra, they don't appear to be linked to one another, but they do indicate here that you should collect them with the same pass energy. So not necessarily the same width, but the same pass energy.
Okay.
And I'll make a note to ask the applications guy exactly why that is. Okay. So if this were all we were going to do in this given experiment, then one other thing we would need to do is insert a gun shutdown at the end of the process. That way, if we walk off and leave this thing to do its experiment, and if I click here, for instance, and go to general, it'll give me an estimated duration for this particular experiment. Right now, as configured, this should take approximately 24 minutes. Okay? So if I don't want to sit here and watch the paint dry for 24 minutes, but I can't come back until, say, a few hours later, I would want to insert this gun shutdown step and say, hey, when you finish doing all this stuff, turn off anything that has a checkbox next to it. And so that would be basically a way to make sure that we were conserving our source lifetime. If, however, I was interested in adding another data point to my sample set here, what I might want to do is go in and say copy all these pieces and make some other kind of a scan. So for instance, I can go here, I can right click on this top right corner, I can copy selected item, and then I can come down here and paste the selected item. Whoops, that didn't work. I don't guess that matters. So this is the top right corner scan. This guy is basically a duplicate of that particular data point. And so if, for instance, I wanted to do a different spot, like maybe somewhere over here on this, what we think is some kind of a weird delamination, I'd be curious to see what this looks like, something different. Over here, say this is another data point of interest right here. Now that I've got this point defined right here, and I'm physically over that new region of interest, I can come over here to my point object position and then hit the read button, and it will change or update the X, Y, Z, and azimuth positions to this new spot. If I hit apply, you can now see that I've got a position here and a position here. And I can again go into this one, go to general, call this top left delamination. Okay. And so now I've got two different data points, and I can go to them if I need to by clicking the move icon, and it'll basically just jot me back and forth between these spots. So again, I can have multiple points under a single source. If I wanted one of these data points here to be measured with a different X-ray spot size or a different flood gun condition, I would have to make a separate source to treat that. But every point underneath here is all subject to the same source. Okay? All right, so we've seen how to add a data point and update that thing's position. Let's go ahead and file, save this experiment. Right now it's under mapping test run. I'm just going to leave it, with the same name. And so this is something that you guys can do, for basically for any of your other specimens, if this happens to be a good set of scans that you want to do. Now, it might behoove me before I go and just launch this experiment that's going to take 48 minutes of time and cost Dr. Zakanoff money. It might behoove me to go in and say at this particular point, where I'm sitting, the top right-hand corner, if I wanted to just take a quick XPS survey spectra and make sure that I am actually seeing features of interest, I can do so here and not have to run every single one of these scans. So once I have a scan selected or some portion of my experiment tree selected, I can click up here on this icon and just run that one experiment step. If you click the generic looking play button, it's going to run the entire experiment. If you click this button, it's only going to run the step that you're highlighted on. Make sense? So let's give that a try. I want to clarify one more time. We are definitely using the flood gun, so he's going to have to turn him on. So we'll have a slight delay after that point. But since we're over here hovering over this spot, let's just see what the survey spectra looks like before we commit all this time. So I'm going to go ahead and click experiment step. It goes up here to this portion, and you'll see kind of a little information about what it's doing. The X-ray source is already on. The flood gun, you can see here, is starting to flash blue, and it'll just go faster, faster, faster until it finally turns on, and then it'll go to solid green. Once that finishes, it'll start taking data, and I'm going to do one other thing that's an important practice, and that is turn off the lights whenever you're collecting spectra. This is particularly true of those people who are working on solar cells, right? If you have the flood gun on, it may or may not compensate for any additional charge buildup if you are generating photo carriers. So if I were you, I would just make sure the lights are turned off. And if I'm remembering correctly, there's a way to make sure that gets done for every single specimen. Okay, so it's running X-ray scan 1 of 2. If I want to see that happen in real time, I can click on the current data view icon right here. And you can see it's just going to sort of plot these guys out. So this is the spectra that it said it was going to collect to survey all of the different elements of interest for what we're taking a look at. Now, this is a little bit sort of like a fingerprint kind of a scenario. So it finished scan number 1, and now it's basically going through pass number 2. When this finishes, I can go ahead and take a quick look at which peaks it identified, and we can just confirm that the elements of interest are in fact present here. And we'll also, I guess, answer the question as to whether or not Craig was right and we do end up seeing the substrate, the tin or the indium. Okay, so it finished that process. You can see that this sort of finished doing what it did. And remember that it didn't execute the entire experiment, so it did not in fact shut down the gun. That's why these are both on, right? Okay, so let's quickly go back into a data grid. I'm going to close this thing. Thank you. Data grid is accessed by clicking on this button. So this is kind of a new processing window. Click here. This opens up a new data grid for me. And the spectra of interest is this guy right here. I could also grab the point and drag it into here, and it would put all of these scans into the data grid for me to sort of take a look at. But right now, the only thing for which I have data is this one. Right? If I try to pull in the indium 3D transition, there is no data there, so it's not gonna let me pull that in. I accidentally copied that. Okay, so within this XPS survey spectra, once you have this highlighted, you can go up here to some of your analysis tools. And for instance, you could just do the generic, hey, computer, find all the peaks for me. Bonk. So it's going to click this thing and dump it out for us. It will then go in and basically take a look at trying to fit each one of these individual species. So it's doing its best to put in what it thinks is a reasonable sort of looking baseline, and then show you that. And from that, it will basically dump out a series of peaks that you see here. The simple thing that you want to check for right now, even though we haven't really done any kind of massaging of the baseline process or its quantification routine, is just check and make sure that you see some kind of a reasonable amount of atomic percentage for the species that you were expecting. And more importantly, you know, in the survey spectra, which I can look at in a larger view here. Oops, sorry, maximize current self. That's this little button right here. Do I see what I was expecting? So boom, I got lead. Boom, I got iodine. I see very little, if any, oxygen. There's some kind of a nitrogen peak. Of course, we got a little bit of carbon. And then there's something going on down here at your valence edge. So does this look like a reasonable spot to continue collecting data?
Yeah.
Okay. And again, if you wanted to, you could go to your other spot, do the same thing, run this one little quick survey scan and make sure that's also a valid point to take data. So let's do that. I'm going to go to my, highlight my data point. I'm going to move to that data point. If I go back to my optical view, you can see that we're translating along here. There we go. There's my little red update. Here we are. Lens back off. XPS survey. Only run this portion, please. And then I can go back to my active view to watch it show up. Once this is complete, I can, of course, have two different spectra in the same sort of field of view right here, and just kind of get a quick idea for whether or not there's major differences there. Once this thing finishes its second scan, then I can do a peak ID, and it will automatically populate them into this peaks set. All right, so that guy finished. That's my highlighted cell. I'm going to go ahead and do peak identification. And as expected, it found sort of the same thing with a little bit less carbon, and it didn't seem to find any oxygen or nitrogen. Well, that's all fine and dandy. Okay, so any last questions about the configuration of this particular experiment?
No.
All right, there's one last thing that we need to do, and that is to ensure that we get the best signal-to-noise ratio, that is the highest number of counts. It's critical that you find the location on your specimen for which you have the highest number of counts. And that means that you're basically at the appropriate Z height position to make sure that your ejected photoelectrons make their way directly towards the detector. So it has to be basically at the appropriate height. Now, we don't have a really great mechanism right now for determining, at least via optical contrast, if we're at the perfect focus position. So it's for that reason that in each of your selected data points, it's important to make sure that you've gotten a rough idea for where you think focus is. And here I can sort of see some particles and some things on the surface. So I know I'm fairly close. You can see right here the updated value of your Z stage position. And then what you typically end up doing is you'll come over here to your data point right here, this top left data point. And within the position screen, I'm going to click on this little guy that says Enable Auto Height. Once I enable Auto Height, I can go into the Auto Height tab and tell it, hey, you, every single time you go to measure at this data point, I want you to scan through this full range. Let's go ahead and increase this just to give ourselves a little bit of play. 500 microns above, plus minus your initial position, which of course is going to be your Z stage position. And I want you to slice it into 21 chunks of 50 microns each. So move the Z stage 50 microns, measure the total number of counts coming into the detector. Do it again, do it again, do it again. Whichever of those 21 positions gave you the most counts, and I don't believe it's at any specific energy. I think it's just raw counts, like how much did you get from all energies. So it's really more looking at like a background. Where did you get the greatest signal to the detector? Set that as your analysis height and proceed to do your scan. Now, of course, if your sample is not perfectly flat, then you want to run this on every single data point that you have. If you're doing a line, you can do it at the center point for the line and basically, find auto height one time for all the different points in the line, or you can have the system find auto height for the starting and end position. So you're doing sort of more like a 2-point line. For areas, same scenario. You can do 1 point for your auto height. You can do 3 points. You can do every single point. It just depends on how much time you want your scan to take. So we've gone ahead and turned on auto height for this first one, the top left delamination, this data point right here. And we've said, hey, I want you to auto height to a relative range of 500 microns in 50 micron steps. We need to do the same thing down here. Say, hey, I want to enable auto height, and I want a range of 500 microns in 50 micron steps. That's how it's going to make sure that it's going to maximize intensity. Okay, so then one more time, I'm going to go ahead and save this experiment. Yes, please. All right. Then I'm going to go ahead and hit the run button. According to the experiment, tree or root, you go down here to the general, and it says this scan is going to take approximately 1 hour. So I don't really feel compelled to make you guys stay on a Zoom session and watch paint dry for an hour. The data will be available on the system whenever this finishes, and again, it will save it into the Zakharov group folder under miscellaneous and this specific test run. So you might ask the question, how am I supposed to get that data off of this computer? And the answer is not with a filthy USB stick, right? What you're going to end up utilizing here is you're going to have to go to web files, and I'll just try to show you briefly what that looks like. So you come in here, webfiles.txstate.edu. If you don't remember this, you can always just go to the Texas State webpage and search for web files. It should be the first hit. But when you try to go to webfiles.txstate.edu, what this is doing is asking for your NetID and your NetID password in order to let you into a browser view of your U drive and also any share drive folders that you happen to have access to. Now, if your group uses OneDrive or Dropbox or whatever else you want to utilize, that's fine with me. Just don't get the data off of this instrument with a USB stick. You've got to move it from the D drive to the cloud. That makes sense? All is clear? You might ask, well, why doesn't it show up, why doesn't it automatically map my network drives when I'm already here? And the answer is because this computer is connected to the internet, but it is not connected to the Texas State domain. So it will not automatically map your shared drive locations here. That's why we have to use web files. Okay. So in terms of the actual, looking at the data, if you need to get access to this Avantage software to do the analysis, you can do that on the Model E PCs that are available in 1202 and 1203. And then per request, we can also look at getting a license for your group to have access to at a computer station of your choosing. We have a limited number of those licenses, so I can't necessarily give one to everybody, but there are also freeware versions of XPS analysis software, which essentially amount to something like a peak fitting software. So any peak fit functionality that you can utilize paired with your own understanding of what you're supposed to be staring at, that will basically allow you to analyze the data. We mentioned one last thing, and that is that the experiment setup right here has nothing to do with data. It's all about procedural, how I'm going to sort of collect things. This type of file has the extension .vgx. X is in X-ray. So the VGX files are what you can use to save the experimental setup. VGD, D as in Delta files, are saved images or saved scans that this Avantage software can open up. If you plan on just importing this into MATLAB or Origin or whatever else you like to use for peak fitting, you might consider saving these guys individually as ASCII type files or CSV type files, so you can just pull in raw data. And then finally, last data type, we talked about VGX for the experiment, VGD for the actual data or scans, including pictures, The last type is a VGP, P as in Peru. That basically saves all of the metadata associated with this kind of, this kind of process, and can also save basically all the bulk scans together in one file. So if you're trying to send something and you don't want to have to send somebody 45 scan files, you can lump it all up into that VGP file extension, and that'll kind of keep it all nice and tight for you. Okay, so if there are no further questions, complaints, or suggestions, or other commentary, I'm going to go ahead and start this guy. So we go up to our experiment. Just one more time, make sure this is saved. And then we're going to go ahead and execute the full experiment this time. So I'm going to click on this guy, the experiment run button. And at the end, it will shut down my guns. And that will leave the tool in a stable state to be able to walk off. So here we go, run button. And it says, hey, somebody was already collecting data in this experiment. That was us, right? We were doing XPS survey scans. Yes, I want to overwrite that data. Thank you. And I'm going to turn off the light. So it's basically configuring all of these different kinds of scenarios. X-ray and flood gun are both going to come on, and you'll see it just start marching through these different pieces here. This is the optimum height. I'll turn this back on so you can kind of see what it's doing really quickly. I'm not sure if it's real obvious, but you can see the stage position right here. It's just moving through those 50 micron steps and trying to maximize its intensity. All right, so just as kind of a recap, please consider going and looking at the Thermo Fisher website. Whenever you build these experiments, the way that you want to think about it is configuring it with excitation source, positions, and then spectra. Excitation, position, spectra, which funnily enough spells XPS, right? Or close enough to it. So remember that little mantra, and that's kind of how you put them together. And then again, once you end up defining a specific experiment and the data you collect seems to provide you the answers you need to do the next step in your research, the basic idea would be to come back and utilize the same kind of experiment over and over again with just updated positions. Okay, so anybody have any other general questions? Here we are in the middle of our lead 4F scan. And you can see it's going to basically go through and do a certain pass. Sometimes you just have to watch this, to see what you're getting. This is a pretty healthy number of counts, so I'm not sure if 10 scans is really necessary here, but you'll see it cleaning up a little bit of the noise right here as it's going across. All right. If you guys don't have any other questions for me, I'm going to go ahead and sign off of the Zoom session.